Hello there, AP Environmental Science class. Welcome to part one of my lecture on Chapter 5, Climate and Terrestrial Biodiversity. This lecture has 60 slides to it, or I think 59 slides. I think I'm doing 25 slides during the first part, so there'll be a little bit over somewhere near low 30 slides for part two. So once again, this is part one, Chapter 5, Climate and Terrestrial Biodiversity. All right, let's get right to it here. We're going to talk first about the African savanna. So why do grasslands grow in some areas while forests and deserts form in others? Well, that all has to do with climate, all right? And we're going to talk about that as we go through this chapter. Basically, the first part of the lecture today will be on weather and climate. Then the second part of the lecture will be on the terrestrial biomes that we're actually going to be discussing as we go through this chapter, or that terrestrial biodiversity, which is the terrestrial biomes that we'll talk about. So again, it's climate. Climate is the reason while areas have grass, some areas have trees, some areas have desert, etc., etc. So type of climate we have basically three types. We have tropical, we have polar, we have temperate climates. We also have wet and dry climates also. Savanna, what is a savanna? Well, a savanna has scattered trees and warm temperatures. Loss of habitat, however, threatens native animals. So we are seeing in many parts of the world the savannas being replaced by other types of biomes because we have a change in the climate in that area. So what's going to happen in a savanna is that you're going to have some rain, more than a desert, but maybe not as much rain as in, let's say, a deciduous forest like here in Ardsley, and you're going to have warm temperatures. So as you change the climate of an area, you unfortunately change the terrestrial biodiversity, because you're unfortunately changing the grasses and the plants and animals and other things that could potentially grow in that biome. And if animals can't adjust or can't evolve quick enough, as we spoke about in the last chapter, well, then those animals unfortunately become extinct. So here we're looking at elephants in the African savanna. Again, a picture many of us are rather familiar with. All right, so what factors influence weather? So there's weather and then there's climate. What I want you to know is weather is more short term, a couple of days, couple of weeks, maybe a month or so, while climate is long term, so really years, decades, centuries, etc. So weather, a set of physical conditions of the lower atmosphere. Most of the weather happens in the troposphere, right, which is the lowest level of the atmosphere. So it's a set of physical conditions of the lower atmosphere in an area over a period of hours to days, right? Pretty much what I just said. And we're going to be looking at atmospheric temperature and precipitation. Again, precipitation, rain, snow, anything falling from the sky. Weather is affected by moving masses of warm and cold air, right? We have these bubbles of warm and cold air moving around the earth. And where they interact with one another, that's going to be your fronts, and that's where most of the weather occurs. Atmospheric pressure changes, be it lower to higher pressure, will affect the weather, and occasional shifts in the major winds. Those are the monsoons that you hear about. Those are affected, or that is affects the weather as well in certain parts of the world. So weather is affected by moving masses of warm and cold air. Again, at the boundaries of these warm and cold air bubbles as they move around are your fronts. Those are the boundaries between two air masses with different temperatures and densities. What is a warm front? Well, a warm front is warm air pushing into cold air. So advancing warm air mass rises up over the cooler air mass that has been at the surface already. Moisture begins to condense as that air rises. This forms layers of clouds at different altitudes and eventually rain or snow. A cold front is when cold air is moving into warm air. The advancing cold air mass stays close to the ground, wedging below warmer air. The warmer air then is shunted upwards. This produces rapidly moving, towering clouds called thunderheads. Most of your cold fronts can cause high surface winds and thunderstorms as it passes through, because that warm air is pushed up rather violently as that cold air pushes into the warm air. Because again, remember, cold air is more dense than warm air. So cold air is going to sink while warm air is going to rise. All right, so moving on. Weather is also affected by atmospheric pressure and wind patterns. So, atmospheric pressure greatest near the Earth's surface, right? What is pressure? Atmospheric pressure is just the amount of atmosphere pushing down on you, right? So, obviously, near the surface, we have the most of the atmosphere pushing down on us. That's why your pressure is greatest near the surface. High pressure air masses contain cool, dense air, usually sunny sky as well. Low pressure air masses contain low density warm air, usually produce clouds and precipitation. Air rises, expands, and cools in low pressure. And that air then condenses when the temperature drops below the dew point. That forms the clouds and then the rain or snow. These are basically cross sections of warm and cold fronts. This is your warm front on the left. Again, warm air moving into cold air. The warm air slowly rides up and over the cool air. So in warm front situations, you mainly have a light, steady rain or snow occurring. Here's your cold front, that cold air mass pushing into warm air, but because the warm air is less dense, it gets shunted up into the atmosphere rather quickly. This rapidly rising air produces showers and thunderstorms, mainly near a cold front. So cold front will have heavier precipitation, but for a shorter period of time than a warm front. A warm front will have steadier precipitation, but it's going to be lighter. So it'll last for a longer time, but usually lighter in a warm front. We also have jet streams, which affect weather around the world, right? These are your powerful winds that circle the globe, basically drive the weather systems with them. They basically are the road maps for our weather systems here on planet Earth, the jet streams. Then we have something called the El Nino Southern Oscillation, otherwise known as ENSO. This is periodic changes in the wind patterns in the Pacific Ocean. This results in drier weather in some areas and wetter weather in other areas of the globe. And El Ninos can alter weather conditions over 2/3 of the world. So here's a little bit more about El Nino. I definitely would understand this chart here. Understand the difference between a normal condition and an El Nino condition in the Pacific. So let's look at the normal condition. Normally, you have cold water up near the west coast of South America. You have the easterly trade winds or the prevailing winds in the tropics moving into from the east. So if you think about that, that wind pushing in from the east actually keeps this warm water out near Australia, right? You can almost think as the wind pushing and keeping the warm water off near Australia and the colder water near the west coast of South America. Because warm air can hold more moisture than cold air, usually in normal conditions, most of your rain, as you'll notice, your thunderstorms are out in the tropical Pacific, and we mainly have drier conditions or normal conditions across the US and South America. In an El Nino year, things change. Those easterly trade winds either die down or sometimes they actually shift and come in from the west. What that allows is all the warm water that was being held out near Australia to now flow towards the coast of South America. So what happens is you end up getting warmer water off the west coast of South America, and this causes more in the way of rain for the United States and for South America, because again, warmer air can hold more moisture. Your warm water causes the air above it to be warmer, which means it can hold more moisture, which means you're going to get more rain. Because that rain has shifted now east, you actually get drought in Australia and Southeast Asia because the warmer water has shifted east, taking the showers, the thunderstorms, the rain with it. All right, so those are the difference between a normal condition and an El Nino condition in the Pacific. Definitely understand this chart. I have seen some FRQs in the past that talk about El Nino, and you'll have to describe it and explain it. So again, definitely understand this chart. This chart shows where during El Nino conditions we usually have a change in the weather. So you'll notice usually in El Nino conditions we get that drought in Southeast Asia. Southeast Asia and in Australia during the El Nino conditions. You'll notice that the southern part of the United States usually gets high rainfall. And for us here in Ardsley, we usually have warmer periods, unusually warm. I would argue that some of that wetness comes up to us as well. So normally in El Ninos, we here in Ardsley are usually warmer and wetter than normal. So my advice here, just understand that El Nino will bring drought to Australia and Southeast Asia and will bring wetter conditions to South America, North America, along with some warmer conditions for North America as well. So if you just kind of know that, you don't need to memorize this chart 100%, but just understand those basics about El Nino and what the conditions will bring around the world, and you should be good to go. All right, moving on. We have tornadoes and tropical cyclones. These are violent weather extremes. So, what is a tornado? It is a violent weather event that forms over land. Vertical convection currents suck air upward, and most of the tornadoes occur in the American Midwest in the spring. Actually, most of the tornadoes around the world occur in the American Midwest. There is another area of high tornadoes in the Central European countries. Other than that, there's not a lot of other areas around the world that get as many tornadoes as we do here in the central parts of the United States. What are tropical cyclones? Those are otherwise known as hurricanes or typhoons, right? If it forms in the Atlantic Ocean, we call it a hurricane. If it forms in the Pacific Ocean, we call it a typhoon. What are they both? Tropical cyclones. They form over warm ocean waters, take a long time to form and gain strength, and their intensity is rated based on the wind speed. That's the Saffir-Simpson scale from 1 to 5, as I'm sure you've seen on the news when these hurricanes threaten parts of the United States. So here is your basic cross section of a tornado, or the anatomy of a tornado, maybe a better way to say it. You'll notice the warm, moist air is drawn in. You have these rising updrafts of air that basically circle very violently. They occur in thunderstorms, tornadoes, and you could get winds over 300 miles per hour in tornadoes. But tornadoes the damage is very small. You can actually have a town where one side of the street is totally demolished. The other side of the street looks like nothing has happened because these tornadoes rarely are more than a half-mile wide. Again, very violent, but in a small area. Hurricanes and typhoons, a big different story, right? These are storms that produce strong winds, not as strong as tornadoes. Usually the winds here, 100, 150 miles per hour at the max. They could get over that, obviously, but usually we don't see winds in hurricanes over 200 miles per hour. The difference is hurricanes are much, much larger, right? So when a hurricane makes landfall, you have damage over hundreds to thousands of miles, not just a half mile like in a tornado. This is how basically the anatomy of a hurricane. In a hurricane, you have warm, moist air evaporating off of the ocean. As that air condenses, it releases energy. Remember your earth science days, releases energy, and that energy then helps to fuel the storm. So basically, hurricanes are fueled by the evaporation of warm water. That's why when hurricanes get up into the northern latitudes where the water is colder, the ocean water, the hurricanes die down pretty quickly, because again, they need the evaporation of that warm water and then the condensation of that water to produce the energy needed to fuel the storm. Okay, so those are kind of the, in a nutshell here, the basics, basics about weather. Now we'll talk about some of the basics of climate, and then again, part 2 of this lecture will actually go into the terrestrial biodiversity, the different type of terrestrial biomes we have out there. So what factors influence climate? Key factors that determine an area's climate going to be the incoming solar energy, how much sunlight an area receives, Earth's rotation, global patterns of air and water movement, atmospheric gases, and the Earth's surface features. So we'll talk about most of these as we go through the next couple of slides. So weather, again, temperature, precipitation, wind speed, cloud cover, hours to days, all right? Climate is the area's general pattern of atmospheric conditions over 3 decades and longer. So again, a much longer period of time for climate. And again, your climate will vary among the Earth's different regions. So what we're looking at here now, these are the looking at Earth's climate zones here, okay? And you'll notice we have polar, subarctic, cool, temperate, highland, tropical, dry, etc. So you can see all over the world here the different type of climate zones that we have out there. So factors that are going to determine the regional climate: cyclical air movement driven by solar energy. I'm going to show you a chart or a picture of that in just a bit. Uneven heating of Earth's surface by the sun, right? This varies with latitude, and that produces the movement of air throughout the planet, right? You have some areas receiving more intense solar radiation on a particular day compared to other areas. So the area receiving the most intense insolation gets warmer. Other areas get colder. That temperature difference allows the wind to start flowing. The tilt of Earth's axis and resulting seasonal changes affect climate. The rotation of Earth and ocean currents actually help redistribute the sun's heat. So first, what we're looking at is something known as a convection cell. This is a convection, very important in the atmosphere. Convection is when warm material rises and cool material sinks. So in this case, we're talking about the air, right? So hot, wet air will rise in an area of low pressure, condense, and form precipitation, either rain or snow. However, under high pressure, that cool, dry air is actually sinking, and that actually causes the air to warm up a little bit and causes the air to dry out. So in high pressure, you usually have sunny conditions. And again, this convection or this convective cell basically drives the weather in many parts of the world. This warm air rising, this cold air sinking, it also redistributes heat around the planet as well. So here are some of the global air circulation that I was talking about. Again, you'll notice moist air rises and then releases into rain. So in certain areas, you have air that is rising, like in the tropics here, right? Air rises, that produces rain. You also have some areas of the globe where air is sinking, and that causes dry conditions. For instance, at 30 degrees north and south is where most of your deserts are located on the planet, and that's because the prevailing wind is sinking at those latitudes, 30 degrees north and 30 degrees south. Again, at the equator, right, air is rising, and that's why most of your tropical rainforests are located at the equator, because as that air rises, it cools, condenses, and forms rain. So you have a lot of rain in the tropics. Same thing around the 60-degree north latitude, north and south latitudes, you get a lot of rain. That's kind of us here in Ardsley, those middle latitudes. And then at the poles, air is actually sinking. That's why at the poles, while it is capped with ice, both the North and South Pole, they actually don't get a lot of snow or ice at the North and South Pole on a yearly basis. It's actually very, very dry, something known as a cold desert, and that's because the winds are mainly sinking at the poles. Again, we have our westerlies, right, our jet streams that carry weather systems from west to east across the earth, and then you have some of those trade winds that in the middle near the equator blow on off to the east. And again, solar energy, highest at the equator, lesser energy reaching the polar area. So understand this, again, the global air circulation, also the solar energy, who gets more, who gets less. And if you have any questions on this, definitely reach out and I can help you a little more. This is the seasonal effects of climate, right? Our Earth's axis is tilted 23.5 degrees from the vertical, and that tilt causes some time of the year the northern hemisphere tilted towards the sun, summer. Sometimes the southern hemisphere is tilted towards the sun, their summer. And while obviously the northern hemisphere is experiencing summer, the southern hemisphere is experiencing winter, and vice versa. So those differences in temperature, right, northern and southern hemisphere, continues to allow that air to flow and continues to affect the climate around the world. Finally, we have the ocean water transport that helps with climate. So you have these currents that actually are throughout the ocean that carry cold water to the north and carry warm water to the south, right? South and north here. So this actually helps redistribute the heat around the globe by these cold and warm ocean currents, bringing warmer water to where it's colder, warming those areas up, and bringing colder water to where it's warmer, cooling those areas down. And this is a way that Earth tries to reach that equilibrium, right? Tries to be the same temperature everywhere. That doesn't happen, obviously. And again, these ocean currents are also going to affect regional climate. In addition, greenhouse gases warm the lower atmosphere. We'll talk more about this. We have a whole unit on greenhouse gases coming up. But as I've said before, I believe in this class, the greenhouse effect is a good effect. If we didn't have these gases warming the lower levels of the atmosphere, the normal temperature or the average temperature on planet Earth would be 0 degrees Fahrenheit, which means no life would have formed on this planet. So luckily, we have these greenhouse gases to trap that outgoing terrestrial radiation, the heat from the planet. It traps some of that heat. The problem is we are adding too many of these greenhouse gases artificially into the atmosphere, which is causing a runaway or a greenhouse effect, I call it, on steroids, that is just causing too much heat to be trapped. So again, a little bit of a greenhouse effect good, a lot of a greenhouse effect is bad. So what are your greenhouse gases? Water vapor, believe it or not, the number one greenhouse gas is water vapor. We don't hear about it a lot because it's not anthropomorphic. We are not creating water vapor and putting excess amounts in the air, but water vapor is a greenhouse gas. Carbon dioxide, obviously, you've heard of because we're putting that into the air. Methane and your nitrous oxide there. Again, the natural greenhouse effect gases keep Earth habitable, but our human-enhanced global warming is what is or our human enhanced of the greenhouse gases putting more into the atmosphere than is naturally there is producing the warming of the globe that we are seeing. Finally, the Earth's surface features affect local climates as well. So we have something called the rain shadow or the orographic effect. This is when mountains interrupt the flow of prevailing winds. Most precipitation will fall on the windward side of the mountain range or the side that faces the prevailing wind. Most of your deserts are on the leeward side of that mountain range or the side on the other side of the prevailing wind. In addition, cities can also have a microclimate, heat islands, for instance. So New York City is always a couple of degrees warmer than we are here in Ardsley. Why? Because New York City is made mainly of concrete, which holds the solar radiation better than grass does. Grass allows that solar radiation to be released out into space, and that's why it's usually a bit colder here in Ardsley than it is down in New York City. Here is that rain shadow or that orographic effect in a visual for you. Again, you have the prevailing wind coming in from the west here, going up the mountain. As the air rises, it condenses, cools into clouds and rain. So most of the time on the windward side, you have a lot of rain, a lot of moisture. Then on the leeward side or the opposite side of the mountain, the air is sinking. That sinking air causes the air to warm and to dry. And so most of your deserts are found on the leeward side of these mountain ranges. So definitely understand the orographic effect or the rain shadow effect here. And again, this diagram here shows it very nicely. All right, so that concludes part 1 of my lecture on chapter 5, climate and terrestrial biodiversity. Make sure to tune back in for part 2. And as always, thanks for listening.